Thank you. And so today we're very happy to have Salil Vadhan from Vadhan, who will tell us about derandomization algorithm via spectral graph theory. Thank you.
Thank you, Thomas. All right, hello everyone. I'm sadly near the end of a visit to Simmery and the University of Sydney, but I've been having a wonderful time. I like this tradition very much that you all have here of the acknowledgement of country. So before beginning, I'd like to acknowledge the traditional owners of Australia and recognize their continuing connection to land, water, and culture. I am currently on the land of the Gadigal people of the Eora Nation and pay my respects to their elders, past, present, and emerging. And I further acknowledge the traditional owners of the country on which you are on, and for those on Zoom, and pay respects to their elders, past, present, and future. Wish we did more of this in the US. And just want to extend thanks to everyone who helped make this visit happen. It's been really a fantastic time. And just want to extend thanks to everyone who helped make this visit happen. It's been really a fantastic time. That's my favorite surfing beach, Curl Beach. But thanks to Thomas Canon, my host in computer science, Jordy and Tillis and Hannah and everyone else working behind the scenes from Simmery, and this also Joachim and Willie from computer science and engineering and all the staff and the faculty, students and visitors. When I planned the visit, I didn't know what activities would be happening at Simmery at the same time. I've really enjoyed the ones that I've been able to engage with, like the Perspectives on Mathematics Culture seminar, and I'm looking forward to the IMU events next week. And I hope to be back soon. All right, so in this talk, there's some recent results that I'll be trying to get to, but really more I want to convey kind of the questions and conjectures in a research area in theoretical computer science around power of randomized algorithms and questions around derandomizing them. And so I'll spend the first part of the talk on that. And then we will see how some of those questions turn very naturally into problems about graph algorithms, which in turn will lead us to tools from spectral graph theory. And I hope to give you a taste of how those mathematical tools are relevant, not only for this problem, but also I'll mention many other places in theoretical computer science. And this is really one of the areas of most fertile interactions between theoretical computer science and pure mathematics. All right, so let me begin with randomization and derandomization. Okay, so back when I was an undergraduate, say back in 1993, the problem in mathematics that captured all our attention, our imagination as students, was Fermat's theorem, which was still an open problem at that time. And suppose back then someone said they had found a counterexample, and they wrote it down, and it was something like this expression I have here of solution to x to the n plus y to the n equals z to the n for some very big numbers. How could we check it? Well, one idea is just calculate. Like calculate those, take those exponents and add them up, and right? It's just mechanical. Why don't we have a computer do it? Like basic arithmetic, computers do this should be a piece of cake. Why? Yeah, the numbers are huge, right? So I've chosen a 20-digit number there in the exponent, okay? And so when we raise numbers to that power, we're involved numbers that have like 10 to the 20 digits, right? So like even that we'd have trouble like fitting that in all the computers in a country. And if I made it 30 digits, no way, not even all the computers in the world right now or in the foreseeable future would be able to store, much less compute on these numbers. Totally infeasible. So any other ideas? Randomization, right? So we want to see the power of randomization. Or anyway, if there's a number theorist in the room, what would you do if you wanted to show that they were wrong? Check it mod p, great. Pick a random prime number. All right, let's pick a 25-digit prime number, a little bit bigger than the exponent here, and check the equation mod p. And then you can do all the calculation. If you do the exponentiation carefully by a good algorithm, you never have to deal with numbers that are more than 25 digits long. Right? You can do mod p all along the way in the calculations. And actually, this is not just like All right, so clearly, if the equation is correct, it will always pass this test, mod p. And if it's not correct, it's fairly easy to show that with high probability over the choice of a random 25-digit prime, you will detect a violation. The equation won't be true mod p, right? And the reason is by just kind of density of prime estimates, prime number theorem, the number of 25-digit prime numbers is much larger than the possible number of prime factors that a 10 to the 20-digit number can have. Because the number of prime factors can most be certainly at most smaller than log base 2 of the number. Okay, and so generalizing this idea, this is one of the kind of nicest and simplest examples of the power of randomized algorithms. It's just this integer identity testing problem, right? So maybe it's not just Fermat's last theorem. Any integer expression where like total number of digits you use is n, and exponents can be using as many digits as you want. The fastest known deterministic algorithm for this problem runs in time exponential in n. Because of this problem, the numbers get really huge. Randomized algorithm, if I haven't messed up on that, I mean, I could be off on the exponent, but I think randomized algorithm can solve this problem in roughly quadratic time in n, right? Basically using the same idea that I talked about earlier. And it's guaranteed not to just work on some instance, on all instances of the problem, the randomized algorithm will give you the correct answer with high probability. Okay, so that's what we mean by a randomized algorithm. And there's many other problems with a similar gap where the best known deterministic algorithm is exponentially slower than randomized algorithms that we know. Some classic examples that involve problems that we also care about in applications and are important in statistical physics are approximate counting problems. So you're given a graph and you want to know how many ways are there how many matchings are there in the graph, ways of pairing up vertices so that each vertex, using edges such that each vertex participates in at most one pair. This has an interpretation in statistical physics of computing what's called the partition function of depending on whether you're talking about matchings or perfect matchings, a dimer system or monomer dimer system. And if you don't know what those words are, don't worry about it. I barely know. Another very classic example is a problem of factoring polynomials over a large finite field. Unlike integer factorization, this is not a hard problem, at least if we allow randomized algorithms. And Berlekamp gave a very efficient algorithm for that in 1970. But it's a randomized algorithm, and we don't know a comparably efficient deterministic algorithm. But the question is this gap inherent? Is there really an exponential gap between the power of randomized algorithms and deterministic algorithms? Or is this just reflecting a deficiency in our current state of knowledge? Maybe there is actually an n squared or n cubed time algorithm for integer identity testing, and similarly for these other problems, and we just haven't discovered it yet. Okay. So surprisingly, if you haven't seen this before, there is very strong evidence that the gap is not inherent. And through a series of really groundbreaking works, have developed what's called this hardness versus randomness paradigm. So the hypothesis is purposely stated informally because I don't really want to get into it in the talk. If the NP complete problems are as hard as we believe them to be, so think of this as something of the flavor, assuming P is different from NP, right? Widely believed. It's not exactly that, a little bit stronger in some ways and a little weaker in some ways. But if they're as hard as we believe them to be, then actually it's possible to take any randomized algorithm that runs in some time-bound T of n on instances of inputs of length n, and convert it into a deterministic algorithm that solves the problem correctly on all instances. And whose runtime is only polynomially larger than the original randomized algorithm. All right, so randomization might make a difference between solving a problem in n squared time and n to the fourth time, but not between, n cubed and exponential. It's not going to make an exponential sequence. Should remark one thing here that kind of often we brush over, but with Ronit in the room, I can't do so. What? No, I think it's an important point to make, is that this is talking about algorithms that run in time at least n, meaning they have enough time to read their entire input. And there is a beautiful body of work on sublinear time algorithms. Ronit's one of the founders of this line of research. And in that setting, randomization does provably help and provide substantial savings in runtime. But for kind of classic algorithmic problems like the ones that I talked about earlier, where we allow reading the entire input, the evidence is going the other way. Okay, and just to give you, it's an entire talk to give you a taste of why this is true, and this is more just motivation for the things I'll be talking about. So here we're assuming that some problems are hard, right? And then using that to kind of make other things easy, convert randomized algorithms to deterministic numbers. Now, why is that? How can we use hardness in a positive way? Well, it turns out you can use the hardness that computational problems have to generate pseudo-random bits, not truly random bits, and pseudo-random bits that no efficient algorithm can tell apart from truly random bits. Okay, so so basically taking the hardness of the problem and turning it into the hardness of telling apart these pseudo-random bits that aren't really generated randomly from truly random ones. And that allows you to then replace the randomness you used in your randomized algorithm with these pseudo-random bits and get an efficient deterministic algorithm. Okay, so a couple of extensions, including just to tell you a little about some of the things that have been happening in the field. With some strengthenings to the assumption that I haven't told you anyway, but still very plausible assumptions. This polynomial blow up in runtime can be made much smaller, not an arbitrary polynomial, but nearly linear in like t to the time to the 1 plus epsilon times n. So you might go from n squared to a little more than n cubed or n cubed to n fourth, but you don't necessarily, the evidence is that you don't need to go from n squared to, n to the eighth. That's not going to be a gap that's that big. And then more related to, really leading to what I want to talk about, there's similar evidence if time is not the resource that we're interested in, but memory. How much memory does the algorithm use? That's called space complexity. So we'll use the word space from now on to mean memory as measured in bits. And the similar evidence under a similar kind of assumption that randomized algorithms can be converted to deterministic ones. And here it's with only a constant factor increase in space usage, not even a polynomial. And that's somehow because we sort of measuring space in a log scale in bits. And so what used to be polynomials turns into constant factors. Okay. And now the goal that I want to talk about is, yeah, these are amazing results, and we believe with varying levels of conviction, depending on which assumption, we believe these assumptions, but just like you all might want to like get rid of the assumption of like, I don't know, generalized Riemann hypothesis in something. We would like to obtain derandomization results unconditionally. Unfortunately, for the case of running time, there's evidence that assumptions of those flavor are necessary, that we will have to make progress on things like the P versus NP problem to get unconditional derandomization. And so the research agenda that I'll be talking about that's been going on for a few decades is for the case of memory, trying to obtain a derandomization result like this unconditionally without assuming something like P different from NP. Okay, so all right, I gave you an example of the power of randomized algorithms when we were considering time, this integer identity testing. Let me give you an example for memory, just to give you a feel of like how randomization can help in memory. Consider, all right, this following problem. My battery is dead on. Use this one for the pointer. So we're given a directed graph, 2 vertices in the graph, a walk length, an integer L, positive integer L, and an epsilon approximation parameter. And the goal is to estimate the following probability. We want to know if you do a random walk starting at vertex S in the graph of length L, what's the probability you end at T? And I want to do that estimated to within plus or minus epsilon. So, you know, another way of saying it is as a counting problem, at least if the graph is all the vertices have the same out degree, out of all the walks of length L in S, what fraction of them end at T? We want to estimate that. All right, so here's a very simple randomized algorithm for it. Let's just do a bunch of random walks of length L in the graph and count what proportion of them end at T. All right, so we keep a counter of how many. We're going to do some number of random walks that depends on the quality of approximation we want. And you start your vertex S. And now just to be clear what a random walk is on a directed graph, in every step of the walk, we go from a vertex V to a uniformly random out neighbor of V, one of the vertices that V is pointing to. And then we see is the final vertex equal to T, and we output what fraction proportion. And the reason we need order 1 over epsilon squared is that the standard deviation of the count here is going to be on the order of square root of T. Okay, and so if T is on the order of 1 over epsilon squared, you'll get an estimate of to within plus or minus epsilon of high probability. Okay, so let's calculate how much space usage. So like normally in graph algorithms, like if you think of things like, suppose I even just want to know, is there a path from S to T? You might do something like breadth first search or depth first search. And you're keeping track of a lot of information. Like for every vertex, you keep marking whether you visited it or not. And so it's like a linear amount of information. The claim is here, we only need a logarithmic number of bits of information to keep track of. We need to keep track of this counter. That's going to be up to log T bits, maybe the index for this loop, log n to keep track of which vertex we're at, log n bits for you know, storing 1 out of n vertices, and log L to keep track of like how long we've walked in a given. Right, and I've forgotten to close parentheses here, but in total, it's log of n number of vertices in the graph, L, the length of the walk, divided by epsilon, memory usage. Right, rather than, for example, linear. Okay, so what's known about getting deterministic space-efficient algorithms for this problem? So what bounds S prime if I'm given, oh, not just for this problem. All right, now I'm going back to the question of, in general, converting randomized space-bounded algorithms into deterministic ones. This was just to give an example of one randomized space-bounded algorithms. So what bounds S prime of n? So our conjecture that we said earlier is that you can always convert one into one with order S of n, constant times S of n memory usage. In the early 80s, it was shown how to get a quadratic blow up in space usage. And then, and somehow that one is not really about randomization. It solves a, the problem, it does this quadratic blow up, even for something that we don't think of, like it doesn't even require that you get the right answer with high probability from the randomized algorithm. So somehow this result is not really about randomization, but this next one, Nissan, and which was then used in this result of Sachs and Joe, got a space to the 3/2 blow up, which is highly non-trivial. And despite a lot of work since then, the only improvement we have is from a few years ago, William Hosa, using some of the ideas that I'll be talking about in this talk, though I won't talk specifically about how William got his result, saves a square root of log S of n factor on that. And we don't know how to improve on the exponent, despite lots of effort. But there's lots of, and you'll maybe get a little taste from the talk, there's lots of variants of the problem that are pushing us closer to, even though it's not captured quantitatively in these bounds, seem to be bringing us closer to the goal. All right, so now let me talk about how we can reduce this general problem of derandomization arbitrary space-bounded algorithms, right, into a very concrete problem about graph algorithms. Right? And basically, it's going to be a problem, this same problem that I introduced earlier as illustrative. Right? So this estimating random walk probabilities, we said it can be done in this logarithmic amount of memory usage. All right, and just noting here, always in space complexity, we only counting the working memory. So your input is bigger, your graph, but you don't, that's just like kind of given to you as a, think of it's on disk or on the internet. You can't store anything there. You're counting how much working memory you need. All right, so it turns out that derandomizing that one algorithm we saw, coming up with a space-efficient algorithm for this one problem, is necessary and sufficient for the general problem of derandomizing space-bounded algorithms. That is, this has a deterministic algorithm with the same space order this space complexity. If and only if you can always convert a space S of n randomized algorithm into one with a deterministic algorithm with only a constant factor larger memory. So this phenomenon that proving something about this like entire class of problems reduces to proving something about a single problem is for those of you who have seen NP completeness, it's the same kind of phenomenon there. You come up with a polynomial time algorithm for the satisfiability problem or the graph recoloring problem. You get a polynomial time algorithm for all NP complete problems. And in a similar way, what I'm saying, what this theorem is really saying is that this problem is complete for randomized space-bounded computation. Okay, and I can show you why. It's less complicated than most NP completeness reductions. So suppose I have a randomized algorithm that uses some space S of n on inputs of length n. If I'm given now an input of length n, x, all right, for it, given that input, I'm going to construct, and I'm putting construct in quotes because you don't really have the space to write this whole, you don't have the space to write this whole graph down. You sort of construct implicitly so that you can kind of read any portion of the graph when another algorithm needs it. You can construct it locally when as needed. But don't worry about that. Don't worry about the details. I think in the rest of the talk, we'll just rush over how things are actually efficiently implemented in space. I want to give you more a taste of the kind of mathematical ideas. All right. So what's this graph? It'll be a kind of a layered graph, a layered directed graph. The height here, which we call it width, is going to equal the number of possible memory configurations of the algorithm. Right? So if the algorithm uses S of n bits of memory, it has at most 2 to the S of n configurations that its memory can be in. And the layers we think of as corresponding to time. We're thinking, the algorithm starts in some initial start configuration. We'll set that to be our source vertex S. And now it's going to compute over time, moving through new configurations. And now we want to know at the end, let's assume it's solving a yes/no problem, does it accept or not? Okay, and so the length here is going to be the runtime of the algorithm, which actually can be proven to be bounded by 2 to the s of n, because otherwise the algorithm would have the possibility of getting into an infinite loop. And now, how do we put the edges there? Well, if the algorithm in some configuration is a deterministic step, it just computes in some way, we just put an edge to whatever the next memory configuration. But since this is a randomized algorithm, sometimes it's going to toss a coin to do something randomly. And when it tosses a coin, we'll put 2 edges, one for each possible heads or tails, which memory configuration it goes to. And that way, random walks on this graph starting at the vertex S correspond exactly to randomized computations of the algorithm. And estimating the probability that a walk of length L started at S ends at T gives you exactly an estimate of the acceptance probability. Okay, and so if, for example, we could solve this estimating random walk probabilities in logarithmic space, we would be able to just do the calculation. The size of this graph is like 2 to the order s of n. We would be able to solve the original problem solved by A in space order s of n. All right, great. All right, so now we're kind of into graphs and directed graphs. So let me just introduce some terminology. We'll use digraphs often for short for directed graphs. I don't know if it'll come up much in the talk, but we allow parallel edges and self loops. Sometimes it's useful. Self loops will come up in the talk. We think of undirected graphs as a special case where whenever you have an edge in one direction, you also have a corresponding edge in the other. And then 2 other subclasses of graphs that come up are regular graphs, where all vertices, there's some number d such that all vertices have both in degree d and out degree d. And Eulerian directed graphs, where every vertex has the same in degree as out degree, but it's not necessarily equal to the same number for all vertices. And so Eulerian graphs are a common generalization of regular directed graphs and undirected graphs, because undirected graphs, since there's no direction, the edges have the vertices have the same in degree as out degree. Right. So one example of the progress that I was mentioning is we are able to achieve in recent work with Ahmadinejad, Kellner, Murtaugh, Peebles, and Sitford, get basically the space complexity we want, logarithmic. There's a tilde there, which is hiding now log factors. Okay, but the exponent is right. It's the exponent of 1. Not in general. We don't solve the general derandomization problem, but we're able to do it for Eulerian directed graphs. Okay, and there's relevant previous work that we're kind of solving somewhat related problems in undirected or Eulerian graphs that were weaker in a couple of ways. So Reingold's theorem and successors from 20 years ago, which was really maybe the first application really of spectral graph theory in this space, was only able to get information sort of about long-term behavior of walks. In particular, like it would allow you to figure out whether vertices are in the same connected component in logarithmic space, but not if you want to know, like estimate the probability that a walk would get there. You wouldn't be able to get a very good estimate of that. And then there's more recent work that was kind of part of this line that led to this paper, where we get much coarser approximations to the behavior of fixed length walks, not the kind that we're looking for here. Details I'll skip over. So now leading up to where spectral graph theory comes in. So our goal is to get high precision estimates of random walk probabilities. What I think I will yeah, I will have time to tell you is how this reduces to having space-efficient algorithms for computing the inverses of Laplacian matrices associated with Eulerian directed graphs, or this reduction works in general, if you can do this with high precision. That in turn reduces to coming up with an appropriate kind of weak approximations to the inverses of Laplacian matrices, which in turn, the tool we use for doing that is really getting into notions of spectral approximation for directed graphs. So just give you a taste of how we're using spectral graph theory. And so I've used this term spectral graph theory. Basically, spectral graph theory is about using linear algebra to understand graphs, and especially things related to eigenvectors, eigenvalues, singular values, and so on. Okay, so I've mentioned these Laplacian matrices. Think of it, the ones that I prefer to work with normalized ones. That would be the identity matrix. So if I have a vertex graph on n vertices, n by n identity matrix minus the random walk transition matrix, the n by n transition matrix for the random walk on the graph. Okay, and so if you want to write it in terms of the adjacency matrix, you could do that together with the diagonal matrix of out degrees in the way that's shown there. And this d out minus a or d minus a, you might have seen as the usual kind of unnormalized definition of a graph Laplacian. I prefer much more to work with this random walk Laplacian. And so here's an example. We have the identity matrix on the diagonal, but we get less than one here because we have a self loop where we're subtracting the random walk matrix. So this vertex has 1/3 probability of going to itself, and the other transition probabilities appear negatively in the Laplacian. Okay, so because W is a left stochastic matrix, that means the column sums of the Laplacian are 0. The stationary distribution for the random walk, that's a probability distribution of the vertices that's invariant under one step of the random walk, is in the kernel of the Laplacian. That's because W pi equals pi and identity pi equals pi. And if the graph is Eulerian, then we know how to read off the stationary distribution. So just for every vertex, assign it probability mass proportional to its degree, and that will be a stationary distribution and unique stationary distribution if the graph is connected. Right, and generally we'll assume that throughout the rest of the talk, the graph is connected. And so the kernel of the Laplacian is one-dimensional, this corresponding to that unique stationary distribution. And in the undirected case, additional nice features of the Laplacian is to be symmetric. Irregular. Let's assume regular. There's a different normalization you do for irregular graphs. It will be symmetric and positive semi-definite. Right, and we won't have those properties in general in the directed case, and that's the kind of cause of some additional effort. All right, so there's been a long line of work in theoretical computer science over the last 20 years on the problem of efficiently solving Laplacian systems. All right, so given graph Laplacian, and you want to solve a system Lx equals b, which is equivalent to being able to either compute or apply the inverse, or more properly, the pseudo inverse, since it has this kernel, to a vector. And this has started in the seminal work of Spielman and Tang, and it's had many applications, and kind of is part of what led to a line of work that now has finally achieved nearly linear time algorithms for the max flow problem, one of the most classic problems in computer science. And most of this literature, though, is focused on different resources than we are. They care about time, not about space. They really want to get nearly linear time algorithms, like linear in the number of edges, number of non-zero entries of the matrix, not like even n squared. And they're for the most part, at least in the first cut, perfectly happy with randomized algorithms. And de-randomization maybe comes as an afterthought. And then really a beautiful line of work, again, starting with Spielman and Tang. And in recent years, a series of works of Cohen et al., well, I don't know, pretty shockingly to me, showed how to generalize the kind of carry out similar kind of algorithmic solutions and generalize the theory to first handle Eulerian directed graphs, and then handle general directed graphs subject to having polynomial mixing time. Think of that as a mild condition that actually holds for the directed graphs we care about. And so that's why we get some hope from what we've managed to do, is that we've managed now for the space de-randomization problem to carry out this first step. And now the question is, can we do the similar reduction or extension from Eulerian to the general case? And if so, then we will kind of solve the de-randomization problem that we set out to solve. Yeah, let me tell you this first step, because at least for me, like first time I see this Laplacian, it's like, why should I care about a Laplacian? What information does that have for me? All right, and this reduction, I think, made me believe in Laplacians. So remember, our goal is to estimate length L random walk probabilities. I'm actually changing it to length L minus 1 just to kind of make indexing cleaner in what I'm going to show you, which you can just think of as your length L random walks correspond to the Lth power of the random walk matrix. And so all I want to do is estimate with high accuracy entries of this high power of W. Right, so we already see like linear algebra make their role. So suppose we're given this directed graph. What I'm going to do is a similar thing to like what we saw before. I'm going to form a layered graph like this, where in each layer there's a bipartite directed graph going from one layer to the next, corresponding to the edges from G. So from vertex 4, I can go to 1 or 2. So I have these. Or 4, so I have edges from 4 to 1, 2, or 4. So unfolding this directed graph, and I'm going to do it L times. Call that the path lifted graph. Let's look at its random walk transition matrix. It's going to be this kind of just below the diagonal have copies of W. It's going to be the Kronecker product of the adjacent matrix of the length L just directed path with W. And this isn't stochastic, it's sub-stochastic, because like random walks do die off if they hit the end. So the column sum is here, not 1, but 0. All right, and so now here there's no more kernel because there's no stationary distribution. Things are all eventually die off. So we can actually just compute the inverse rather than the pseudo inverse. But yeah, so let's do that. And now we can just use the power series formula for the inverse, which is going to be, 1 plus x squared plus x cubed, so on. Okay, so basically this is walks of length 1 in the path lifted graph, walks of length 2, walks of length 3, and so on. And here it turns out to have a very nice structure. So because of this path lifting, the walks of different lengths don't interfere with each other. Right? This walks of length 1 from here can only go to this layer. Walks of length 2 can only go to this layer. You have walks of length 1 appearing just below the diagonal, walks of length 2 below that, walks of length 3 below that. And aha, in the lower left corner is the matrix we're interested in computing accurately. Okay, and so this gives us a reduction to computing this accurately to computing the inverse of a Laplacian of this substochastic matrix. All right, but we said we're gonna work with Eulerian graphs. This graph's not, even if our original graph was Eulerian, it's not quite Eulerian because the first layer and the last layer, right, have no incoming edges, no outgoing edges. There's a simple trick to deal with that. You just add a new vertex here that connects the beginning and the end, and call the random walk matrix of that thing W hat. And now that's actually stochastic a matrix. So it doesn't have its Laplacian is an inverse, but from the pseudo inverse, turns out that you can compute what are called escape probabilities. So the probability a random walk from, say, vertex S visits T before it visits V. You just look at the 3x3 submatrix of ST and V, and you invert that 3x3 matrix, and you can compute this thing. And that's exactly now, again, the probability that we want, because if we visit T before visiting V, then you haven't used any of these sort of fake edges that we added. Great. All right, so I think I'll spend a couple minutes to I want to get to the little bit of spectral graph theory, but then I'll end. So we said we're going to, if we get a high precision inverse of a Laplacian, we can compute the probabilities we want. Say it's going to suffice to get a weak approximate inverse. What do we mean by a weak approximate inverse? What's good enough for us? Sometimes referred to as a preconditioner in the numerical linear algebra world. All right, so what I want is a matrix P that's kind of like an inverse, where if I multiply P times L, I get something that's close to the identity, close in some norm. And what I need it to be is a submultiplicative matrix norm. Right, so could be L2 operator norm, but usually we'll need to change basis or something and get some somewhat different norm. And so just to bring out singular values that will come up in a moment. This is equivalent to saying, or it suffices to have under some basis the largest singular value of the identity minus PL be bounded, if I say it. Okay, and these conditions are not good enough to read off entries. Like you can satisfy these conditions, and a single entry is going to be useless to you. Okay, and why is preconditioning useful? It turns out then we can write the inverse that we're interested in. Here I'm writing it, pretending that inverses exist. Similar thing with pseudo inverse, just notationally cleaner. By using the usual power series expansion, but we've kind of like multiplied by P and then and then removed it. And what you get here when you have this preconditioner, because identity minus PL has norm smaller, bounded away from 1, you get a very quickly converging series here. And so in relatively few terms of this, you get highly accurate estimates. And this is a standard tool in numerical linear algebra, preconditioning. All right, so now how are we going to get a preconditioner? Well, just to give you intuition, things are a little more complicated than this, but again, think of the power series, pretend it's actually substochastics and power series. We can write it as our usual power series, but more convenient now is to write it in this infinite product form. Identity plus identity plus W, identity plus W squared, identity plus W to the 4, with just powers of 2 in the exponent. And the idea that goes back to Hung and Spielman in the undirected case is we're going to try to compute some spectral approximation of these powers of W that appear in this product, right? Powers by all powers of 2. And take as our preconditioner the product of the identity plus those. And so what does it mean now to spectrally approximate? Reaching kind of where I wanted to try to get to. So for undirected graphs, Spielman and Teng introduced this notion of approximation that turned out to be, again, extremely useful and led to very rich literature. So let's restrict attention to regular graphs now, just to avoid normal. Otherwise, you have to do some normalization by the diagonal matrix of the stationary distribution. They said, well, we just asked that the Laplacian of your approximation, your graph that approximates it, is within a 1 plus or minus epsilon factor of the Laplacian that you want to approximate in the loner order on PSD matrices, right? So this is like one matrix and this really only makes sense for symmetric matrices. One matrix is less than another if their difference is PSD. That is, the quadratic form defined by A is always smaller than or equal to the quadratic form defined by B. Okay, and there's some equivalent ways you could write it. This last one is kind of leads naturally to the one that I wanted to say for directed graphs, which is here. This is called, we call it singular value approximation. And what we've done compared to the previous definition, if you have only one test vector and you look at the quadratic form, you lose all the asymmetric information in the graph. It doesn't depend. The ijth entry is not distinguished from the jth entry. So first thing we need to do is have different test vectors on the left and the right. And then the question is, what do you measure error with respect to? Previously, it was like norm of x squared minus x transpose wx. And what we replace it with here is this norm squared of x transpose w. And then we do a similar thing for the test vector on the right. And what these are capturing is what we call mixing of the random walk from x and y. So just to think of two examples, if I start y concentrated at a point, and this is the complete graph here. There's two extreme examples, and I do one step of the random walk from y, I will get to the uniform distribution on the vertices. Right, so I completely mix. And correspondingly, the length of y squared minus the length of wy squared is very large. It's 0.8, as large as can be. In contrast, consider this graph that has, it's kind of a directed tripartite graph. All the edges from these two vertices go to these two vertices. All the edges from these two go to these two. All the edges from these two go to these two. And suppose we start concentrated on two vertices, and I do a step of the random walk, I'm going to end up concentrated on these two vertices. And there's no reduction in the length. I'm not mixing at all. I'm not more uniform on the graph. And what this is requiring is when you don't mix at all, you have to approximate perfectly. When you mix a lot, you can be quite coarse. So we are running out of time. So let me just say this has the preconditioning property, and it has a lot of other nice properties that previous notions didn't have. Preserved underpowering with no loss in the approximation. You can hit the matrices on the left and right with arbitrary bounded norm matrices and preserve approximation. It implies that singular values, not only eigenvalues, are well approximated. Okay, and let me stop here. I didn't expect to have time to tell you a little bit how we achieve it. There's also a nice reduction from directed to undirected approximation. And one of the main tools we use here are things called expander graphs. If you've heard of them, that maybe I'll just flash this slide up. That's in a picture. This is what was supposed to be in the poster, picture of a Ramanujan graph, and constructed by Lubotsky, Phillips, and Sarnak. And this has been one of the tools for constructing expander graphs, have been one of the areas of very fruitful interaction between, again, theoretical computer science and pure mathematics. So to conclude, hopefully the examples at the beginning convinced you randomization is a powerful tool for algorithm design. But we believe, and with good evidence, and are trying to prove unconditionally, that it can actually be removed at low cost in the basic model setting for algorithms. Okay, and then there's important exceptions to that. Like I mentioned, sublinear time algorithms, distributed computing, cryptography. There's other places, types of problems and models we consider in theoretical computer science where randomization is provably necessary. Okay. And finally, as a spectral graph theory is one of the, again, areas where pure math and theoretical computer science have had a lot of interaction. And one of the places it's very powerful in theoretical computer science is as a tool for de-randomization. Let me stop there. Thank you.